Hello and welcome back. In the last video, we discussed 3A, state Newton's third law of motion, but in the interest of time and because the bell was about to ring, we called it a day there. But if you're back, this is the continuation of question 3 from paper 2. And it looks like we're dealing with some momentum conservation. So as a quick recap, Newton's third law of motion says that forces exist in pairs, and those force pairs are equal in magnitude, opposite in direction. The forces are equal in magnitude, opposite in direction. And we went on to discuss how those forces have to be of the same type and how the forces always act on two different objects. There's plenty of examples of equal and opposite forces that are not a Newton's third law force pair. So click the link above if you want to see that end of the last video. All right, so we've got a block X of mass m sub x slides in a straight line along a horizontal frictionless surface as shown. Show that there. And it says the block X moving with speed 5v collides head-on with the stationary block Y of mass m sub y. The two blocks stick together and then move with a common speed v as shown. Use conservation of momentum to show that the ratio m sub y to m sub x is equal to 4. All right, well, they pretty much tell us how to do it, so it shouldn't be too hard at all. So the conservation of momentum says that the initial momentum equals the final momentum. And since this object is stationary initially, we don't really have to consider its momentum. Let's just consider the momentum of object X there. And so we have mass X moving at a speed of 5v. So kind of have like, that's the initial momentum. And we could write it like 5mxv if we like. That's going to equal the final momentum. And so we have this object over here, which is a mass of mx plus my, right? Sticks together at a common speed v. All right, so that's what the conservation of momentum says. And it says the ratio my to mx is equal to 4. So somehow that's got to have a ratio of my to mx equal to 4. Well, let's just sort of trust the mathematics here and see what we can do with it. I'm going to distribute this v. So I have 5mxv equal to mxv plus myv. Now, what I'm trying to do is really get this ratio here. The only place that my shows up is right here. So I kind of want to like work with that. One thing that I could do right away is just divide everything by v. Okay, if I divide by v, gets rid of the velocities, or you could say, well, v divided by v is 1. 1 times this is just this, right? So we rewrite it 5mx equals mx plus my, like that. And then let's see here. If we were to subtract an mx from both sides, then we'd have 4mx equals my. And if we divide each side by the mass of x, then we get this ratio my to mx, and on this side we have 4. So there you go. Curly vectors showing you what's going on there, right? Let's clean that up a bit. So once you divide both sides by m sub x, then you've got the ratio on the right side, and we can show that it is indeed equal to 4. So not too bad there. What I'd really like to do is calculate a ratio of kinetic energies, though. I mean, that would be something nice. Yes, calculate the ratio of the total kinetic energy of x and y after the collision to the total kinetic energy of x and y before the collision. Just what I was looking for there. All right, so let's remind ourselves that after the collision, we have a 1/2 mv squared, right? And they had a common speed v. It's the sum of the masses there. So that's the kinetic energy afterwards over the kinetic energy before the collision. Well, that's going to be a 1/2 mx. And it's going at a speed of 5v squared. Just have to sort of keep track of that. Remember that y was stationary, and so it has no energy of motion if it's stationary. So we can sort of ignore y there for before the collision. All right, let's go ahead and 1/2 divided by 1/2 is 1, and 1 times the rest is just the rest. And then I'm going to distribute this v like this. And so I'll say mxv squared plus myv squared over mx 25v squared, right? So you square everything inside of that. So we get sort of this. Down here, it looks like we have a common denominator. Another thing I could do is sort of cancel out the v squareds there, right? So that's going to just sort of cancel out. But I could separate this back out. So it's like mx over 25 mx, right? And then I could keep the v squareds and cancel it there. Plus right, so it's kind of like we have this common denominator that I could sort of separate out like this, and this might be a little bit easier to sort of work with here. Let's see, so I have mx divided by mx is 1, so over here I have 1/25 plus my over mx. Now we just, a moment ago, we showed that the ratio my to mx is 4, right? So I could kind of just substitute that, and so this ratio my to mx is 4. So I saw that 25, and so I have 1/25 plus 4/25, it's 5/25. And so there's your ratio right there, 5 to 25, or you could report it as a decimal, 0.2. So the ratio of the kinetic energy after the collision to before the collision is 0.2. The question goes on to read, state the value of the ratio in 2 for a perfectly elastic collision. You may recall that a perfectly elastic collision is one where the kinetic energy is conserved, right? So there'd be just as much kinetic energy after as before. The ratio would just be 1-to-1 or 1. So that's why it's only 1 mark, because it's pretty straightforward. You just have to remember what a perfectly elastic collision is. And then we have the variation with time t of the momentum of block X, shown in the figure 3.3 down there. And it's telling you that block X makes contact with block Y at a time of 20 milliseconds. Described qualitatively, since we don't need to quantify it, the magnitude and direction of the resultant force, if any, acting on block X in the time interval. So the first one is considering 0 to 20 milliseconds. And it looks like there, the momentum is non-zero and it has yet to change. And so there's no force yet, right? Remember that the rate of change of momentum is force. And so because the momentum is constant, there's no change in momentum, so the force would be 0. It's like, what's the direction of a force of 0? I'll leave that for you to consider. Between 20 and 40 milliseconds, it's clear that the momentum is now changing, and so that requires a force. Block X is moving to the right this way, and so the force would be acting on it to the left, right? So there would be a non-zero force, right, changing its momentum, and it would be acting to the left. It wants both the magnitude and direction of the resultant force. And then it says on figure 3.3, sketch the variation of the momentum of block Y with time t from 0 to 60 milliseconds. And that's 14 total marks for this question. So this was a lengthy one. Now block Y, you may recall, was stationary to begin with, and so it had 0 momentum. For the first 20 milliseconds, it has to just sort of stay at 0 there, right? So that's going to be what's happening initially. If we kind of, let's actually do this. Let's zoom in on this so we can see the gridding in the graph paper a little bit more clearly. So we know that the block Y would have 0 momentum initially for the first 20 milliseconds. And then here is where they make contact. You could note that block X, whose momentum is represented by this line right here, drops down 1, 2, 3, 4 of these sort of, not the large squares, which would be here to here, but sort of like the half of those large squares. And so we just want to keep the same change in momentum, that this thing is going to increase 1, 2, 3, 4 of these squares this way. And so by the time that they're done interacting, right at this point, you can kind of see the momentum of this thing is leveled off. And so it's just a straight line sort of between those two. And then that's the momentum transfer. Now we can kind of look at this and say, you're telling me that block X and block Y have different values of momentum after the collision, even though they stick together. Remember what we showed previously in this question is that block Y has 4 times the mass of block X. And so while they share a common speed V, right, we know that block Y, whose data is represented by this line that I just sketched, is 4 times more massive. And that's why it has 4 times the momentum, because it has 4 times the mass. Momentum, remember, is the product of mass and velocity. And so that makes sense there, that each block could have a different value of momenta, even though they're traveling at the same speed v. This has been another worked example with Dr. Schleif, and I'm still living the physics life. See you next time.